Sorry about that. Let's try this again. All right. Construct the proof or sequence for the tree shown here. So what we want to do here is find the smallest leaf that's on the tree and write down what its parent is. So my leaves right now are 3, 7, 5, 9, and 8. And so the smallest parent is 4. Okay. And so now we're going to remove 3 from the tree. And we look for the leaf now that is the smallest leaf. My leaves are now 8, 7, 5, and 9. 5 is the smallest, and its parent is 6. So now we remove 5. So now my leaves are 8, 7, and 9. 7 is the smallest, and its parent is 4. So we remove 7 from the tree. All right, so now I've got this going from 2 down to 1 down to 8, and then 2 down to 4 down to 6 down to 9. 8 is my smallest leaf now, and its parent is 1. Okay. 1 is now my smallest leaf, and its parent is 2. And now that 1 is gone, 2 is a leaf. I mean, it wasn't originally drawn that way. It was drawn as if it was the root. But after I've deleted all the edges in this way, 2 is now the smallest leaf, and its parent is 4. And now 4, 6, and 9 are connected, and 4 is now a leaf. And 4 is the smallest leaf, and its parent is 6. And then once we're down to just 2 vertices left, they're both kind of leaves, they're both kind of parents. It's not easy to tell which one's the parent and which one's the leaf. We don't write down anything once we're down to the last 2 vertices. And so we get 4, 6, 4, 1, 2, 4, 6. All right, let's move on. So number 17, let's look at this graph here. We want to use Kruskal's algorithm to construct a minimum weight spanning tree for W. All right, so what we want to do here is start by picking the smallest possible edge. And so that's going to be the edge of weight 1. So I'm going to label some vertices here, A, B, C, D, E, F, and G. All right, so using Kruskal's, we're going to add the edge with weight 1 from A to B. All right. Then we'll go down here and add the edge of weight 2, which is from C to D. We'll add the edge of weight 3, which is from F to G. So far, no problems. The edge of weight 4 from D to G. 5 from D to E. All right, we can't add the edge of weight 6 because that would create a cycle, C, D, G, F, and then back to C. And so we do not use the edge of weight 6. So we have to use the edge of weight 7 instead. And that's the edge from A to C. And at this point, notice that all of my vertices are connected together. B to A to C to D to E to G to F. That is, I can go all of these vertices. But if I didn't notice that and I kept going, 8 would create a cycle from A to C to D. 9 would create a cycle from E to D to G. 10 would create a cycle from A to B to D to C and back to A. And 11 would create this triangle down here, D to F to G and back. And so all of the remaining edges create cycles. Okay? All right. So let's move on. Let's use Prim's algorithm to construct a minimum weight spanning tree for W. All right. So if we use Prim's algorithm instead, we pick some starting vertex. I'll go ahead and start with A. And of all the edges that come out of A, 1 is the cheapest. So I'll add AB with weight 1. And now, coming out of either A or B, I have choices of 7, 8, and 10. 7 is the cheapest. So I'll add AC next. All right, now coming out of A or B or C, my cheapest edge is 2 from C to D. All right, coming out of all of these different vertices, the cheapest edge I can find is the 4 that gets me to G. And then the cheapest edge that continues on is 3 from G to F. And then 5 from D to E. And at that point, all the remaining edges will create cycles. And so we stop. We ended up getting the edge of weight 7 very early on in the process, but that's okay. We got exactly the same tree that we got before. Okay? All right, number 18. Use the Ford-Fulkerson algorithm to find a maximal flow. And I can't see the additional copies on this slide, but let's go ahead and work through this. So we need a path from A to H. So let's start at the top. Let's go across A to B to F to H. And the bottleneck is 3. A to B is 3, B to F is 5, F to H is 4. So we can add 3 units along this path. And that can't get any more along that path. So now there's not a single path along the bottom because the path from D to, that goes from A to D to F doesn't hit G. So let's go A to D to F over to H. Actually, let's go straight to the middle first. A to C to F to H. And then we'll go across the bottom. So now my bottlenecks are capacities of 2. So I can add 2 more units there. A to C, C to F, F to H. Okay. All right. So now if we go down across the bottom, A to D to F to H. My bottleneck capacity is 0 because I can't go from F to H. Sorry, that's not a good example here. So what else could we do? We can go, we can't go up from A to B. We can't go from A to C. If we go from A to D, we have to go on to F, and then we would have to go on to H. And so I think we're done. Is that right? So our maximum capacity in this case is, looks like it's 5. There's no way to improve that unless, is there some way we can do some backflow? How about, let's see. No, we can't do that either because if I go down here, and this is the only way I can go from A right now, I can't backflow along this edge because it's empty. I could back up to C because this isn't empty, but I can't then back up to F because I can't go forward to F because that's yeah, we can do that. How about that? All right. So let me highlight this in blue. This is why you want to be careful about Ford Fulkerson here. There we go. All right. So what I'm going to do is I'm going to, my bottleneck is 1 unit. So what I'm going to do is add 1 unit to this row, at this edge, add 1 unit to this edge, subtract a unit from this edge, add a unit to this edge, and then add a unit to this edge. Okay? The reason why this works is that we're now taking these 2 units, instead of sending them both along C to F, we set 1 along C to, or I've got 2 F's, that should probably have been an E. 1 up here, and then that could use as the last of the 4 in my capacity here. And then that freed up a unit down here along this one to allow an extra unit to flow along there. So we got 1 more unit from A to D to F to C. It bugs me that both of these are F's, so I'm going to make this an E, and that'll be an E, and that'll be an E, and then an H. And we got 1 more that way. But at this point, we really are stuck, because if I tried to send 1 more unit out from A, it would have to go down to D, because this edge is full and this edge is full. This is the only edge that's not full. But from D, it can't go anywhere because this edge really truly is full. And so we're at maximum capacity. Max capacity is 6. All right. That's tricky. Let's move on. Determine whether this graph contains an Euler tour. If I look at the degrees of the vertices, all of the degrees are 4. And so since every degree is even, the answer is yes. The graph contains an Euler tour. Now, that's all the question has to do is determine whether it contains an Euler tour. You didn't actually have to find one, but an example of one would be to go around the outside of this shape and then how do we want to do this? I want to incorporate these triangles as well. So let me back up a moment. So start from this vertex, go around the triangle first, then go up to the next vertex, hit that triangle, then up to the next vertex, hit that triangle, and now all of the triangles have been covered, and then we'll just finish going around the circle that way. Okay? So that would be an Euler tour. Number 20, suppose we have a graph that has an Euler trail from vertex A to vertex B, but does not have an Euler tour. So I've got some vertex A, I can trace all the way through the graph, and then get to vertex B, but I do not have an Euler tour. I don't have a way of getting back to the starting point. Does that mean that G cannot contain the edge AB? This is false. The easiest example is just the graph that contains A and B and nothing else. I have a trail that goes from A to B, and then I don't have a way to get back to the starting point because my graph is simple. And so this contains AB, but doesn't have an Euler-Tor. Okay? So, but we don't have a way of getting back from B to A. All right, let's move on. For which values of Kn, for which values of n does Kn have an Euler-Tor? So I want to show you a couple of examples here. K3 is just a triangle. And the degree of every vertex is 2, because every vertex connects to the other 2 out of the 3 vertices. And since every degree is even, this has a tor. But if I go through K4, the degrees are now odd. Every vertex connects to all the other 3 vertices out of a 4 total. And since the degrees are odd, this does not have an Euler-Tor. And now I think you can see where we're going. Anytime I look at Kn, however many vertices I have, the degree is always n minus 1. And the degree has to be even in order to have an Euler-Tor, and so n has to be odd. And so the answer is all odd values of n. Okay. All right. Somebody applied Hierholzer's algorithm to this graph and identified the walk. Where is my... Oh. I don't want to show y'all what I just did. That was stupid. A to B to F to I to H to E to D and then back to A. So then the next step in the algorithm is to choose a vertex that allows us to continue the algorithm. Which vertices are suitable for this purpose? The requirement is that the vertex the vertex is adjacent to some used edges and unused edges. That's the requirement for Hierholzer's. And so A is not eligible because it only adjacent to edges that we've already used. And C is not eligible because it's only adjacent edges we haven't used yet. So we have to have a vertex that touches edges that are used and are not used. So B has edges that we've already used and edges that we could continue with. So B would be okay, not C. D would be okay, E would be okay, F would be okay, and H would be okay. And so any of these 5 vertices would be suitable for continuing. Okay? All right, the graph from problem 22 does not have a Hamilton cycle. So let's explain why not. So let's reproduce that graph here. And then it's got 2 diagonals here and here. All right, there you go. In order to have a Hamilton cycle, every vertex must be included. Exactly once. So to incorporate A as part of the Hamilton cycle, then the edges AB and AD must appear. And this is a hint. Find a list of edges which must appear. That's the only way to get to A, is to go get there from B to A to D or D to A to B, but we have to use these two edges. Well, the only way to get to C is to use the edges BC and CF. And the only way to get to I is to use FI and IH. And the only way to get to G is to use HG and GD. Also must appear. But these edges already form a cycle. And we haven't included E. So it's a cycle that doesn't include E. And there's nowhere to connect E. If I connect E up to B, then this vertex has a degree of 3, and that's not a cycle anymore. And so once you list the edges that have to appear, you already have a cycle, but it's left out one of the vertices. Okay? All right. Last example. Why is this graph not planar? So let's look at the graph right here that contains all the vertices, say, except for C. So G minus C is has these three vertices D, E, F, and then the other two vertices A and B, which I'm going to put here and here. A connects down to D, E, F, and B connects to D, E, F also. So G minus C is planar. But now we have to place C somewhere to get G again. So if we were going to place C here, then we have a problem because there's no way to get from C to E without crossing a boundary. So we can't draw CE. So this edge would be a problem. If we put C here inside this region, then I can't get over to D. I can go CE, I can go to CF, but I can't go CD. So from here we can't draw CD. And we could try putting C over in this region, but we can't get from this C to F. And so no matter which region we place a C in, the outside region, the right side, or the left side, there's always one vertex we can't connect to. And so this graph is not planar. All right. Good luck on the exam tomorrow, and enjoy the rest of your weekend. Take care.